Okay, so we're going to take a look at our next tracker lab. So I'm going to walk you through exactly what we're going to be doing. We're going to take a close look at an object rolling or sliding, is what we're approximating it as, sliding down an inclined plane, and we're going to assume that it has pretty much no friction. Now, we got that set up with one of our low friction carts inside the lab, while you all were working with friction with the inclined plane setup that we have. Now, we've got Tracker open, and if you use the video that I provide for you, you can either find it on the Google Drive, take a look in our online system that gives you the link to that, or if you're using the computer that I'm recording this on, then you'll be able to follow the instructions that I have right here. So I'm going to go up to File, I'm going to go to Import and Video. Now, it may come up in the Tracker folder. I noticed a bunch of people who kept clicking on Tracker icon PNG and getting confused. That's not the thing you want. I'm going to close tab. No, don't save don't save that. New tab. Sorry for the small diversion there, but had a lot of people running into problems with that. We do not want tracker icon .png. I'm going to click the desktop button up here. We're going to go to the folder marked Tracker Labs. It's actually on the desktop. Oops, clicked one too many times on the name. That's okay. I'm going to click over here. Double click on that, that looks fine. And for this one, for the inclined plane, we're going to take a look at Tracker Lab number 4. Now this is the Tracker Lab that we're doing with forces. I told you all in class, my mouse is acting a little weird, sorry about that. I told you all in class that we do a Tracker Lab basically with each of the sections, at least with mechanics, usually to supplement something that I tell you. So, or that we've found by running through our mathematics, and then we want to try and verify that it's happening in the real world. Now, sometimes it can be really difficult to collect all of that data in the real world without fancy equipment, and that's where us using Tracker comes in. Now, I apologize, for some reason the light is catching this weird and we can't really read the note card on there, but this is set to a 30-degree angle. You're welcome to take a picture of this, put it into, well, what I did was PowerPoint. I drew some lines along here, and then you can double check that it should be right at about 30 degrees. You also know that way up here is 45 degrees and way down here is 0 degrees, so we can see, even if you don't take my word for it, we're pretty close to 30 degrees. All right, now what's going to happen in this video is I have hit play, and I'm going to come around, and this is all in slow motion. And I'm going to put one of our low friction carts on there, and it's going to fall down. So we know that it's somewhere around the 600, frame 600 range. So it looks like it's in motion in the 540s. What I'm going to do is I'm going to click back a little bit. Now remember, when you click a few times, you may have to wait a moment for the computer to catch up. This isn't a supercomputer. This is actually, it's a decent enough computer, but it's not much more powerful than a standard laptop, not even like a gaming laptop. All right. Anyway, so I can see my hand coming backwards in here as I go scroll back down, and looks like my fingers are coming away right at around frame 530. And then let's see. I'm going to go forward. My hand goes flying forward, so 530 will be where we start. And let's go to 575. I don't know if it's hit my sweater yet, but it's looking pretty close. So I'm going to come up to the film strip here. I'm going to begin at frame 530, and I'm going to go to frame 575. Now, one of the things that I'll point out while I'm here, we're going to set this up hopefully that you can get auto track and you wouldn't need to do this for any of the future ones. But instead of going one frame by one frame, you could also click in here and change the step size and tell it, okay, every time we move forward, I want you to skip a couple frames. I could put in step size of 3 frames. We're going to use auto track, so leaving it as step size of 1 should be fine. Although if you find for whatever reason you can't do auto track and you have a very large video like we often do, instead of clicking on 45 data points, you might set it to maybe 3, at which point you'd have to click on 15 data points, although you'd have a bit more space in between them. Okay, here we go. Okay. We're going to do exactly the same thing that we've done before. I'm going to rewind the video to the very beginning, back over here. New very beginning, I should say, so frame 530. I'm going to teach. I'm going over from the film strip. I'm going to go over to our scale, calibration scale. I'm going to teach it how long a meter is. That's why we always try and set it up where there's a meter stick inside our field of view, or at least something that we can get a sense of reference on. If you have a setup that you need to record and you don't have a meter stick set up on that, if you've got something very nearby the action, say maybe you, for instance, depending on what the video may be of, you could always measure your height later, convert that into meters and centimeters, and then drag a little bar along you. I could also use the length of this cart if we wanted to, but like I said, we usually set it up with a meter stick. Just adding a little bit of information in case you wanted to do this on your own later with other things. I'm going to do a coordinate axis here. We've got a greenish bluish dot on our tracker cart. I'm going to put the origin right on it at the very beginning. And just like we did before, so that I can try and get all of my motion in one direction, I'm going to take the x-axis here. I'm going to put it down on the cart at the end where that little sticker is. So I fast forwarded and then dragged this down. Now also when we go through and we do our analysis, what I've done here is I've now got, because this one is my positive x-axis, I have now directed my positive x-axis down the incline. And you'll notice that my y-axes are now over here. I don't know which one's which, but for that matter, we don't actually have to care about which one is the positive y-axis. I think it may be this, but not terribly important. We're not going to look at anything in the y, because by doing this, we've set up all the motion in the x direction. So I'm going to go ahead and hide that, and here we go, point mass. Now, with this one being high speed, don't need you to click 45 times. We're going to hold down Control and Shift. We get a circular crosshair, and I'm going to put it right on that green dot. Now, I'm going to drag this over to the side because I like to watch whenever it's tracking. Some of the videos that we're going to have from here on in, they might get a little bit messier when they track, and you want to watch them to see if, for some reason, the computer starts tracking something it shouldn't. Now, this one should be fine, but I'll warn you again in the future for some of our next ones. I'm going to go ahead and click Search, and I'm going to watch the sticker there, stay under. And it's doing the auto track for us because of me clicking a bunch of times. There we go. Looks like it was able to track this just fine, thankfully. I'm going to go ahead and click Close, and we've got our data here. Now, I know some students were having some issues with it, and we're going to start using this more and more. Down here in our table, it gives us the time data, it gives us the X position, and it gives us the Y position. Now, by default, it brings up the X position versus time. Watch what happens when I click here. I can ask it for the Y position versus time. Now you'll notice it seems to change a little bit, but see this up here? It says times 10 to the negative 3. That means that all of these are laughably tiny numbers, which is why you see a bunch of zeros over here. In fact, when you scroll down in the Y column, it's basically a whole bunch of zeros. Nothing but zeros. There's one that's there's some that technically aren't zero, but they're really tiny compared to what we're working with. In short, nothing is going on in the Y. It might go up or down a little smidge, but that's mostly because of the tracking stuff we've got, or me not necessarily getting my coordinate system right. I'm going to switch this back to X. We can see there's a lot of good data in the X. The Y is just noise. We're going to hit Table. See, it brings up whatever we have a check mark next to. I can uncheck Y, and it disappears. It gets rid of it. I could check VX, and here's where it would put in the velocities that it's measured for the X direction. We're not actually going to use that, so I'm going to go ahead and remove that. You're welcome to play around with it if you'd like, but you're going to notice that since it calculates it, let's see, VX. We've got a pretty good line there, but we have some bumps and wiggles here and there. That's why I prefer that you all deal with the time and the position data, because that's something that it measures directly from that. Okay, I'm going to come down here, highlight all these again. You can right-click, you can do copy selected cells as formatted or full precision. Doesn't actually matter. Then I bring up Excel. I'm going to paste these in. Paste. There we go. All right. Be back in just a moment where we're going to pick up with this. Okay, so we've just finished pasting in the data, but I do want to go over what we're going to do with the data first. So let's go back to what we covered in class. Now I'm going to go through this pretty quickly, check your class notes to follow up on this, but we looked at deriving the general solution to a mass on an inclined plane with no friction. So we've got here an inclined plane in blue. You can see the green box mass on top of it. In fact, let me bring this in, mass of m, and it's inclined at some angle theta, and I'm going to mark on here that it is frictionless. Now, what we found in class, just the same as we did a moment ago, that it was going to be much easier if we pointed our positive x direction down the inclined plane and put all of the acceleration in the x direction. That would result in the y direction being pointed up off of the inclined plane. Now over here I have my free body diagram with a dotted line to represent the surface of the inclined plane. We have the force of gravity that pulls straight down, and we have the normal force, normal meaning 90 degrees, that points up 90 degrees off of the inclined plane. Now that we've got those set up, we can actually start splitting them into components. Why do I want to split them into components? Well, we'll see in just a moment, and hopefully you already know. I've replaced the force of gravity with its equation, mg. We've got theta right here, as we discussed in class, this angle between the force of gravity and the new y-axis, specifically the negative y-axis, is the same as the angle of incline. We looked at some of that in class where when this angle goes to 0, this angle goes to 0, and when this angle goes to 90, that angle goes to 90. You can draw it out, do a little bit with geometry to prove it to yourself if you'd like. Now, since this is theta, my y component is actually the adjacent side, so it will be mg cosine theta is the value of whatever this y component is. My x component, however, is mg sine theta. Now that we've got those components, we can apply Newton's second law. Sum of forces equals mass times acceleration. And since we're adding forces, we need to split them into components, x's and y's. So we have the sum of forces in the x is equal to the mass times the acceleration in the x, and the sum of the forces in the y is equal to the mass times acceleration in the y. So here we go. I thought I leveled these out a little bit better, and yet here we are. The sum of forces in the x, well, the only one we've got in the x is positive mg sine theta. Positive because it is pointing down the inclined plane, and that's the direction that I set to be positive. Now, since that's the only force in the x direction, it will be equal to the mass times the acceleration in the x. Now, in the y direction, we have the normal force, which is positive, the way we've got it set up for our positive y direction, minus negative mg cosine theta, which is the y component, and those together will be equal to the mass times the acceleration in the y. Now, once again, our cart is not jumping up off of the inclined plane, nor is it sinking into the inclined plane, so it is not moving or accelerating in our new y direction. And I can't emphasize this enough. It's the y direction set up by my coordinate system in this problem, right here. This y direction, not vertical, not straight up and down, because it is moving partly down, but because I've set up my coordinate system differently. That means my acceleration in the y in this weird coordinate system is 0, which is actually the point because it puts everything, all the action, in the x direction, so I don't have to solve both of these at the same time. This gives me the following, that my acceleration in the x, which is my actual full acceleration, will be equal to g sine theta. You can get that by dividing both sides by the mass. We find that the mass drops out, and it doesn't matter how heavy the object is, it should actually follow this, at least in ideal physics world. We also find over here, in case you had to work with friction, the normal force is equal to mg cosine theta, because our acceleration in our y is 0. All right, so we end up with our acceleration in the x is equal to g sine theta, which brings us back to the thing that we were just analyzing. Well, we're on Earth, so g should be pretty close to 9.81, and we measured that before with our very first tracker lab. I told you, and you saw in class, that I set this up that it's at an angle of 30 degrees. So we have our acceleration we expect to be, with no friction, 9.81 meters per second squared times sine 30 degrees, and that should get us somewhere in the ballpark of about 4.91 meters per second squared. It's actually 4.905, but I don't expect to be accurate to 3 significant figures anyway, so as long as we're in the ballpark of about 4.9 or 5, that sounds great. Now, that's if there is no friction. Now, I told you that those carts that we have are low friction, but they're not no friction. Regardless, we expect our acceleration to be somewhere in the ballpark of high 4s, maybe 5 meters per second squared. All right, This brings us back to something you've seen before. I'm going to go through it a bit faster, but just like us dropping the puck, because I've effectively dropped this cart when I let go of it, we have the same kinematic equations that we did before. Now, we can apply these whenever the acceleration is constant, and we expect the acceleration to be constant because we expect it to be constantly about 4.9 meters per second squared. So, we can actually apply this kinematic equation. Once again, our initial velocity is equal to 0, and that cleans this up where we get the relationship delta x equals 1/2 at squared. Now we want to linearize this, just like we did in the very first one. You're going to see that we're going to make a very similar graph to the very first tracker lab. But we want, for a linear response, we want y equals mx, where y is going to be our vertical data point, and x is going to be our horizontal when we graph them. Now, we could do delta x versus t squared, and the slope would give us 1/2 a, but, as I mentioned before, just like we did with the other one, we can also do delta x versus 1/2 t squared, and our slope will actually be outright our acceleration. So that's what we're actually going to do, okay? So, here we go. Now we're going to bring this up in Excel. Here's the data points that I just pulled in from the lab that we were doing. I'm going to make another column, like we did before, 1/2 t squared, just so I've got it marked. And that means I'm going to teach this some math. I'm going to say equals 0.5 for 1/2 times t, and then I'm going to put in a little caret by shift 6, and then 2 for raised to the second power. Now last time I had you click on the box 2 times. Both of them are perfectly fine, whichever one you'd rather do. I switch between the two periodically. I will say when I get to cubes or bringing it up to 4 or 5 or anything other than squared, it's usually faster to do the little caret, but that's okay. All right, so we're most of the way there. Insert, once again, over here, the scatter plot, scatter x, y. And then we're going to use the first one, the little dot one. I'm going to drag this up. Let's go select data, right-click and select data. Add. We're going to do series name, delta x, or I'm sorry, last time we did position versus time 1/2 time squared, and then I can put Sanchez, my name. It's up to you, but I do want to be able to identify to whom it belongs. So our x values are horizontal. We said that our horizontal axis was going to be 1/2 t squared. I'm going to hit OK. And then my y values, that's going to be my position. So I'm going to drag down and select all of, those. So I've got one extra here. I'm actually going to hit backspace right here when I've got this selected, and then just do 48 instead of having to drag the whole thing over again. This should be fine. I'm going to click OK, and we can see, hey, look at that. We end up with our data in a pretty straight line. I'm going to select the data, right-click, go to Add Trendline, just like we've done before. A linear fit looks great, and we're going to do Display Equation on Chart, and I'm going to get rid of this. And we get the following. I'm going to scoot these over some. I now have that y equals mx plus b. You'll notice that the plus b is really small, 0.0084. That's effectively 0. It pretty much goes through 0, 0, which is great. We've got a nice, pretty much straight line, and it has a slope of about 4.77 meters per second squared. Now, one thing that I'll bring up is, just like we mentioned before, it is not, let me jump back to it, 4.91-ish, somewhere around here. There we go, 4.91-ish. Remember, 4.91 is if there is no friction. Now, I said that these are low friction carts, but they do actually have a little bit of friction. So, are we surprised that we ended up with a little bit less? Well, not really. In fact, if you want, you could go through and solve this. I know many of you won't, but for good practice, you could solve what the acceleration should be with friction and use our numbers to actually try and get me a measurement of the coefficient of friction for our little cart. You should find that it's pretty small. In fact, I did some measurements of it doing exactly this, and for this I found it to be probably about 0.08. Now that's not 0, but it's a pretty small number. All right, let's go ahead and fix this up just a little bit, just as we did before. Let's see if we can clean up our axis. Let's see. Design, add chart element. Oh, and putting names on there and so forth. So format, let's see, design, add chart element, axis titles, primary horizontal, and we'll do, I don't necessarily need the full thing, but it does help to have 1/2 times squared. However, the main thing that I'd really like is seconds squared so that we have the units. So I'm going to kind of cut this one a little bit short. It is up to you exactly how much detail you want to do on this, but we do want to clean it up some. At the very least, we want some titles that tell us our units. And so this one is in meters. Great. All right, here's where I can change a little bit of this, even back out, well, yeah, let's just do this the smart way. Okay, so I'm going to format axis. There we go. That's bringing that back, which is what I wanted. Number. Because right now it's putting it in scientific notation, which is fine, I guess, but it's a little weird. So I'm going to do number 2. That sounds great. And what I mean by number and then 2, decimal places 2. I could put this to decimal places of 1. And you'll notice that, hey, that looks perfectly fine too. So it's whichever you would do. Or if you would prefer 3 decimal places. It depends on what your data looks like. Now I've got at least a couple of these that have 2 significant figures, so I'm going to put it as decimal places of 2. So that way we've got 0.35. And that's great. On this one, I'm going to do the same thing. Oh, in fact, it's already over here. So let's go to scientific. Let's go to number. My eyes are crossing a little bit. There we go. Number, 2 decimal places, maybe 3. Nope, looks like 2 probably has all the information that I want and is going to make it look much better. All right, and then the last thing that I am going to look for is vertical axis crosses. That one's set at 0, so I'm going to have to go back over to the other one here. You'll notice that my x-axis is up a little bit. Nope. Actually, it's just an optical illusion. Everything looks, is it? Oh, I see what it's doing, because it goes down to a minimum of negative 0.5. I'm going to put the minimum at 0, and then, yeah, that looks much better. That's why it was acting a little weird. All right, and then this is the graph that we're looking for. The last thing that I'd like you to do is take a look at this. Your actual value, in my case, it's 4.77. Does that sound reasonable, and how does it match with what we'd expect? Well, our slope should actually, let me copy this in. You don't have to do this, but I can copy this. And then that's what this last page is for. I'm going to paste that right in there. And we've got my graph. So we got 4.77, and we were expecting 4.91. Those are actually really close to one another. And so we could go through and do a bit more comparisons on that. Part of this may also be significant figures. But the biggest reason is we've probably got a little bit of friction in there. And that's going to lower our acceleration a little bit, because we would then, if you think about it, back up here with our sum of forces, we would have minus the force of friction, but it's probably going to be very small because of a very low coefficient of friction. Regardless, this is what we've got. Here's the graph that I'm looking for here, and we can see that it is very close to the expected value for g sine 30 degrees. All right.